Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about how to estimate the population mean using so-called student's t-distribution. If you remember previously, we discussed that we can estimate the population mean using sample statistic. We take a sample, calculate its mean. It appears sometimes we can't really just take a lot of items into the sample. So the sample size might be 5 items or 10 items. Well, in this case, when the sample size is less than 30, we are going to use so-called t-distribution table. Let's do a review a bit what we have discussed so far. So previously we say that, hey, if you would like to estimate the population mean, you take a sample, you calculate the mean of the sample, for example, it is going to be equal to the 2. You calculate so-called error margin, it is going to be equal to the 0.1, it is something like 10%. Then you add the 0.1 to the 2, subtract the 0.1 from the 2 in order to create the interval. So our interval is going to be between 1.9 and 2.1. That's going to be our confidence interval for the population mean. Well, if the error margin is going to be different, for example, if the error margin is equal to the 0.5, in this case, our interval is going to be bigger. So we take the same sample, we calculate the mean, it's going to be 2, we calculate the error margin, it is going to be equal to the 0.5. Well, in this case, the interval is going to be larger, right? You see, so the length of the interval around the mean, x bar, defined by this so-called error margin E. Higher the value of the error margin E, the higher the interval, the length of the interval is going to be longer. Well, what is the formula of the error margin and what basically defines the values of the error margin? So the formula for the error margin is equal to the ZC, the critical point, times the sigma divided to the square root of n, where n is the sample size. Well, the error margin is inversely proportional to the sample size. The bigger the sample size, the smaller the error margin. So for example, if you've calculated that the error margin, let's say, is equal to let's say that the critical point is simply 1, the sigma is equal to the 2 divided to the square root of 100. So your sample size has 100 items. At the same time, the E is going to be equal to the 1 times the 2 divided to, let's say, 400. Okay, well, you see, so in the second case, the n, the sample size, is bigger. But at the same time, if I would calculate this, it is going to be equal to 2 over 10, which is equal to 1 over 5, right? And the second case, it's going to be 2 over 20, which is equal to 1 over 10. So in the second case, E2 is smaller than E1. So if you increase the sample size, the error margin is going to be decreased, so your interval, which you're estimating, is going to be smaller. So, well, this is what we want. So we would like to have a better and better estimate of the population mean. So in this case, smaller interval would be considered as a better estimator. At the same time, the error margin depends on the confidence interval as well. So the smaller the confidence level, the smaller the error margin. So for example, if you would like to be confident for the 90%, then the critical point is equal to the 1.64, I guess. Then the E is going to be equal to the 1.64 times the sigma divided to the square root of n. So let's assume that it is going to be some constant. At the same time, if you would like to be confident for 95%, then the Z is going to be equal to the 1.96. The error margin is going to be 1.96. So let's denote this 1 and 2 times the same constant, sigma divided to the square root of n. So, well, depending on whether you're choosing C to be equal to the 90% or C to be equal to the 95%, your error margin is going to be different. Well, in this case, the error margin for the higher confidence level is bigger. So it means that if you would like to be more and more confident about your interval, you need to choose the interval bigger and bigger, which totally makes sense. So now it appears when the sample size n is smaller than 30, so is bigger than 30, we are going to find the critical points using so-called Z table. So it was given in the criteria in the algorithm of the confidence intervals from the previous lecture. But what if the sample size is less than 30? Well, in this case, we are going to use so-called student's t-distribution table. And the only thing which is going to be changed in all of our procedures is the formula for the error margin. So instead of multiplying the critical point ZC to the sigma and divided to the square root of n, we are going to multiply TC. So the critical points are going to be found from the t-tables. Well, what is the t-table actually? So the t-table is the series of the curves, while the z-table is just one curve, and you're given one table which finds the areas under the same curve. The t-table is going to depend on so-called degrees of freedom, which is going to be equal to say n minus 1, where n is the sample size. So if your sample contains like 5 items, then degrees of freedom is 4. If your sample contains 12 items, then degrees of freedom is 11. So it is always going to be n minus 1. Well, depending on the degrees of freedom, you're going to have different curves. If the degrees of freedom is equal to the 25, you're going to have one curve. And in order to find the critical points, you're going to find the t-points from the table. Again, the confidence level is the area under this t-curve, right? So which is going to be the area in the middle, so that the two areas on the tails here, on this tail and here on this tail, are going to be the same. So this is how we are going to choose this. Well, it appears the t-table is not just one curve, it is the series of the curves. If you choose the degrees of freedom to be equal to the 25, you've got this curve, but if you choose the degrees of freedom to be equal to 8, you're going to have a different curve. You see, so this curve is a little bit lower. And if you now choose the area to be equal to the c, so c, let's say, is equal to the 90% or 0.9. So your critical points are going to be different, right? So since this curve is lower, you need to shift your critical points wider. You need to take them wider here. So because the area should be the same. Your curve is becoming a little bit lower, so that is why your critical points are going to be wider. So you're going to have different critical points depending on the curve as well, for the same value of the confidence interval. For example, if the degrees of freedom is equal to the 3, it is going to be even lower. In this case, your critical points are going to be even wider, right? So for the same value of the c, so let's say 0.9, you're going to have different and different critical points depending on the degrees of freedom, depending on the sample size. Well, how to find them technically? So technically, you will be given a table, and you need to find them from the table. Well, this table consists of the degrees of freedom and to the confidence level. So here you've got the confidence level to be equal to the 0.5, 0.8, 0.9, 0.95, and so on. Well, at the same time, so if you would like to find the critical point which is about the sample, so in order to if you would like to find the critical point for the sample with 5 items at the confidence level 95%, you just need to go to this table. You need to choose the confidence level to be equal to the 0.95. Then you need to find the degrees of freedom to be equal to the 4, which is n minus 1, the sample size minus 1. Then you find this point at the intersection. It is going to be your critical point. Well, what does it mean? It means that if you would have this curve, the t curve, right? So if you would choose this area to be equal to the 0.95, then this point here would be equal to the 2.77. And this point would be equal to the minus 2.77. So this is how you find the critical points for the t-table, using the critical points. So the same as, like, let's do another example. So let's say you would like to find a critical point which corresponds to the 95% of level of confidence when you have a sample with 12 items. Again, the degrees of freedom is going to be 12 minus 1, which is 11. You find this from the first column. Then the degrees of freedom, so the confidence level is going to be equal to the 95, because you're given the 95% level of the confidence level. You find a correspondence, you choose the intersection of these two rows and columns. You're going to find a critical point to be equal to the 2.2. Again, if you would draw the t-table or t-curve, this point here, 2.2 and minus 2.2, is going to contain this area, C, 0.95. So please note that the whole area under this curve is equal to the 1. Well, this is how we're going to find the critical points. I would like to ask you to remember this point, 2.2, because we're going to use this in our next problem. So let's solve the problem. So let's say you are given the population, and you would like to estimate the mean of the population. It's difficult to take a lot of measurements from the population. For example, sometimes it is difficult to measure some test, blood test. So let's say for the insulin. right? It is really difficult because the person whom you're taking the blood test should not eat for at least 12 hours. So let's assume that we've been able to take this test for the insulin for only 12 persons. We measure some level of the insulin there. Then there are here the measurements: 84, 14, 583, 50, 0, 57, and so on. There are 12 measurements, 12 items of your sample. So you are going to have the population. You would like to know what is the mean of this population. In order to do that, you choose a small sample from this population and you calculate the mean of the sample. Your sample here consists of only 12 items. Here are all of the 12 items. In step number 1, we calculate the mean. In order to calculate the mean, you have to sum all of these values, starting 84, ending 57, and divide this to the 12. So this is how we calculate the mean, and this is going to be equal to the 106.25. Well, the step number 2 is to find the standard deviation. If you remember, the meaning or the definition of the standard deviation is the average distance between all of the points and the mean. Well, in this case, I'm going to subtract 106.25 from every point, from 84, from 14, from 583, and so on. Well, it is going to be 84 minus 196. I think it's probably 196 probably here. So there was a typo. 196.25 in the square, 14 minus 196.25 in the square, and so on. We're going to do this for all of the points, and at the end we're going to divide this to the 11, not to the 12, because we're calculating the variance or the standard deviation of a sample. If you do all of these calculations, it is going to be equal to 27 thousandths. But please note that we found S in the square, which is the variance. And the standard deviation is going to be the square root of the variance. So if you calculate the square root of this to 27 thousandths, it is going to be equal to the 164.33. Well, this is how we find the mean and the standard deviation. We need them in order to construct the confidence interval. So we are going to construct the confidence interval around the mean. If you remember, plus minus error margin. And in order to calculate the error margin, we need the following terms. In order to calculate the error margin, we need to know the critical point times the standard deviation of the sample divided to the square root of n, which is the sample size. Well, if you need to construct the confidence interval with the confidence level 0.95, you need to find the critical point from the t-table, where you need to know the c and also the degrees of freedom, which is equal to the 11. Well, if you remember in our example to find the t, we found this already, and it was equal to the 2.2. Well, I'm just going to substitute this to here, so 2.2 times the standard deviation of the sample divided to the square root of 12, which is the sample size. It's going to be equal to the 104.421. Well, I'm just going to add this to the mean and subtract this from the mean in order to construct the confidence interval. So our mean of this population, the whole population, is going to be within this interval, and I'm confident about this interval for the 95%. Well, this is how we are going to construct the confidence intervals for the population mean, in order to estimate the population mean when we are able to take small samples. But everything is not so clear, so there is a huge algorithm which we have to fulfill. So it is not like you are going to use the t-table always whenever the sample size is less than 30. You have to fulfill or follow the following algorithm. Well, so all of these processes which we're discussing are pretty much algorithmic. So you need to just simply follow the algorithm in order to estimate the population mean, proportion on the variance. And in this case, when you are going to do this for the population mean, you have to follow the following algorithm. So first of all, if you would like to know whether you have to use a z-table or t-table, you need to check whether the sample size is more than 30. If it is more than 30, you don't bother yourself. You're going to use the z-table. You're going to substitute the sigma in the formula of the error margin with the standard deviation of the sample. But if not, it is not so easy. So you need to first of all check whether the population distribution is normal. Again, so if you take, so you're going to have the population, you took a sample from the population. When the sample size is less than 30, you've been able to make the measurements of less than 30 items or 30 persons. In the first case, you need to know what is the distribution of the whole population. So usually, for example, if you would like to estimate the average IQ scores of people, you would assume that the IQ scores have a normal distribution, which is a really good assumption. Or for example, if you would like to estimate the average height of people, you can assume that the heights of people have the normal distribution, which is a really good approximation. But if not, you can't really just construct the confidence levels or confidence intervals. If n is smaller than 30 and if the population doesn't have a normal distribution, then we cannot do the confidence intervals. But if yes, if the population have the normal distribution, you need to do one more check whether you know the population standard deviation by some reasons, by the previous experience or some knowledge about the population. If you know the population standard deviation, then you still use the Z table. But if you don't know this, you're going to use the T table. You see, so you need to fulfill lots of no's in order to be able to use the T table. Well, this is the general guides how to choose which table we are going to use, either the Z table, either the T table. But no matter which table we are going to use, the general procedures in order to construct the confidence intervals are going to be the same. The only thing which is different is how we are going to find the critical points, either Z, either T, and we are going to use simply T tables. Well, this is how we are going to construct the confidence intervals for the population mean when the sample size is less than 30 and we don't know the sigma. Thank you very much for your attention. I hope that this was helpful for you.